Okay, if you're an A&P student right now, deep in your airframe course, you've probably just hit or are wading through Chapter 3, Aircraft Fabric Covering. And, this isn't just some history lesson.
Not at all. It's absolutely fundamental to the airworthiness of thousands of aircraft out there flying right now.
Right, so what we want to do today is really pull apart the critical stuff, the technical knowledge, the history that got us here, and maybe most importantly, the legal requirements you have to know. Not just for your exams, but for actually signing off an aircraft.
That's exactly the mission. This isn't just about, identifying different fabrics. It's about understanding the whole system. We're going from those really early flammable dope coatings all the way to modern polyester systems that last, well, almost forever if done right.
Yeah.
And for you as an AMT student, understanding the regs around fabric work repairs, alterations, it's incredibly strict. You've got to know the materials evolution, the rules like STCs, and the hands-on details of putting it all together and testing it.
I think the big story here, really, is this constant push and pull in engineering. I mean, fabric's big win has always been its weight, right?
Yeah.
Super light. That's why we still see it on gliders, LSA.
Absolutely. Weight is king in those applications.
But the early downsides were huge, like existentially huge. One, extreme flammability. Two, it just didn't last out in the elements.
Exactly. And pretty much every single innovation we're about to talk about was aimed squarely at solving those two core problems. Everything flows from that.
Okay, so let's dive in. Where does it start? The very beginning.
Well, the pioneers, the first sort of viable systems, they relied on organic fabrics. We're talking finely woven stuff, usually Irish linen or really high-grade cotton.
Yep.
But right away, there was a problem. As soon as you put these fabrics out in the air, they sagged, like really badly.
So not tight against the structure.
Nope. Loose fabric flapping around. It left the airframe underneath exposed to everything, and it totally messed up the aerodynamics. Plus, it looked terrible.
And that exposure means deterioration, right?
Yeah.
Fast.
You got it. So the first attempts to fix this were, well, kind of basic. They just coated it with oils, varnishes, trying to seal it and maybe tighten it up a bit.
Didn't work too well, I'm guessing.
Not really. The big breakthrough, the thing that really defined fabric covering for 50 years, came around 1916, and that was aircraft dope.
Dope. Okay, what exactly is dope?
The first big one was nitrate dope. Chemically speaking, it's cellulose, basically plant fiber dissolved in nitric acid. It creates the sort of liquid plastic film.
And what did it do for the fabric?
Oh, it was transformative. First, it stuck really well to the linen or cotton fibers. Second, it protected the fabric from dirt, moisture, you name it. And third, this was key, as the solvents evaporated, it shrank a lot.
So that's what pulled the fabric tight.
Exactly. It tautened the fabric right over the airframe, giving you that smooth, durable aerodynamic finish. Huge advantages.
Yeah.
But, and this is a massive but, extreme flammability. I mean, terrifyingly flammable. Think old movie film reels, that kind of volatile. An aircraft covered in nitrate dope could go up in flames incredibly easily. A real safety nightmare.
Wow. Okay, yeah, that sounds like something you'd want to fix. Fast. So what was the next step?
The search for something safer led straight to butyrate dope. Different chemistry. This time it was cellulose dissolved in butyric acid. And the main reason for developing it was specifically to cut down on that intense fire hazard of the nitrate stuff.
Okay, so safer. That's a big win. Any downsides?
There always are, right? The butyrate, unfortunately, just didn't stick to the fabric fibers nearly as well as the nitrate dope did. It was a trade-off.
You needed the stickiness and tautening of nitrate, but the safety of butyrate.
Precisely. Which led to this really pragmatic, kind of common-sense solution that became the standard for organic fabrics.
What was that?
A combination system. You'd put down the first few coats using nitrate dope, get that good adhesion, get that initial tautness. Then you'd follow up with the main heavier coats using the less flammable butyrate dope.
Best of both worlds, sort of.
Pretty much. It significantly cut down the overall fire risk compared to straight nitrate, and it became the go-to method for years.
Okay, so flammability is somewhat managed. What about the other big problem? Durability. Did the dope fix that?
It helped, but a new enemy emerged. The sun. Specifically UV radiation.
Ultraviolet light.
Yep. Turns out, UV rays went straight through those clear dope coatings, and they didn't just damage the fabric over time, they actually degraded the structure underneath, whether it was wood or metal tubing. The UV was basically slow cooking everything.
Okay, that's bad. How did they fight that? Paint.
Well, regular paints didn't bond well with the dope finish, so the clever fix was to add aluminum solids, basically, tiny aluminum flakes directly into the butyrate dope top coats.
Like adding glitter, but for protection.
Kinda, yeah. These aluminum particles acted like millions of microscopic mirrors, reflecting the UV rays away. Applying a couple of coats of this aluminum pigmented dope was essential. It protected the fabric, and crucially, it shielded the airframe structure from that UV damage. Became mandatory, really. You see that silvery look on a lot of older planes? That's often aluminum dope.
Right, I've seen that. But even with the aluminum protection, the organic fabric itself still had limits, didn't it?
Oh, definitely. Even with the best care, cotton or linen on a plane that was actually flown regularly would only last, ballpark, 5 to maybe 10 years before the fabric strength dropped below safe limits.
5 to 10 years. That's not very long in aircraft terms.
Not at all. And that short lifespan, plus the fact that proper grade A aircraft cotton basically disappeared from the U.S. market over 20 years ago, well, that really pushed the industry forward.
So metal skins took over for bigger, faster planes.
Right, aluminum was stronger, more aerodynamic, but for applications where lightweight was absolutely critical, lighters, home builts, light sport aircraft, and those classic utility planes like Cubs and Champs fabric was still the way to go. They just needed a better fabric.
Interpolyester.
Exactly. The modern solution really took hold in the 1950s with polyester fabric. You probably know it by brand names like Dacron. This stuff basically solved the durability problem overnight.
How so?
Polyester fibers, unlike cotton or linen, don't rot. And when you protect them properly from UV, they essentially last indefinitely. Their strength holds up way, way longer.
Okay, indefinite lifespan sounds pretty good. But could you just slap the old nitrate butyrate dope onto this new polyester?
Well, they tried, and it caused problems. What happened was the old dope systems would go on, okay, shrink the fabric tight, but then over time, the dope would get brittle and start to peel or separate delaminate from those thick polyester fibers.
Ah, so the coating failed before the fabric did.
Precisely. The fabric was outlasting the coating system designed for organic materials. This meant they needed totally new chemicals, new systems designed specifically to stick to polyester long term.
So what did those modern solutions involve?
Couple of key things. They developed dope additives called plasticizers. These get mixed into the dope to keep the final film flexible, even when it's fully cured, so it doesn't crack and peel off the polyester.
Makes sense.
And they also formulated non-tautening dope formulas. These are designed primarily for sealing and protection without causing excessive shrinkage, which could also pull the coating away from the fabric substrate.
So the result is a system where the coating lasts as long as the fabric.
Pretty much. A modern polyester system, properly applied and protected, is way stronger and far more durable than any cotton or linen system could ever be. It's the standard now for fabric aircraft for very good reasons.
Okay, that covers the material evolution. Now, let's shift gears into something equally critical for you as an AMT student. The legal side, getting the paperwork right.
Absolutely crucial. Mess this up, and it doesn't matter how good the fabric job looks, the plane isn't airworthy. It starts with the aircraft's original type certificate, the TC.
The manufacturer's original approval.
Exactly. The basic rule is, when you replace fabric, you, the mechanic, must use the same materials and the same techniques that were approved under that original TC, period.
Unless you get specific permission from the FAA to do something different.
Right, because the fabric skin is considered part of the aircraft's certified structure. You can't just change it without approval.
And given everything we just said about polyester being better lighter, lasts longer, stronger, probably cheaper in the long run, pretty much everyone with an old cotton-covered plane wants to switch, right?
Of course. The advantages are huge, but making that switch legally requires navigating the FAA's requirements very carefully.
So how do you get approval to use, say, a modern polyester system on a plane originally certified with cotton?
There are basically 3 approved pathways to do this, to deviate from that old TC data.
Okay, path number 1.
By far the most common today is using a supplemental type certificate, or STC.
I've heard of those. That's like an add-on approval.
Essentially, yes. An STC is issued by the FAA, usually to the company that makes the fabric system, like Polyfiber or Seconite. It certifies that their specific system, their fabric, tapes, glues, chemicals, is safe and compliant to use on a specific list of aircraft models. Say, a Cessna 170, originally covered in cotton.
So the STC gives you the recipe.
It is the recipe. It's the Bible for that job. It tells you exactly which brand of fabric, which tape, which glue, which primer, which top coat to use, and crucially, the exact procedure you have to follow.
And you can't deviate. at all.
Not one bit. If that STC says use brand X glue and you use brand Y glue because you ran out, that aircraft is technically unairworthy. The STC is legally binding down to the last detail.
Wow. Okay, that's strict. What's path number 2?
This one's less common and generally more work for the mechanic. It's called a field approval.
Field approval. Sounds like something you get locally.
You do. It's a one-time approval granted by your local FAA Flight Standards District Office, the FSDO, for a specific alteration on a specific aircraft. You request it using FAA Form 337, the Major Repair and Alteration Form.
So you, the mechanic, have to make the case.
Yes. You have to submit detailed documentation outlining exactly what materials and processes you plan to use, and you need to provide engineering justification, often referencing data from sources like Advisory Circular 43.13-1, to prove to the FAA inspector that your proposed alteration is at least equivalent in safety and performance to the original certified design.
That sounds like a high bar.
It can be. The FSDO inspector has to review and sign off on your plan before you start the work. It's definitely more involved than just buying an existing STC package.
Okay, STC field approval. What's the third way?
The third path is the cleanest, but it depends on the original aircraft manufacturer. It's a Type Certificate Datasheet Update, or TCDS update.
So the manufacturer updates their own paperwork.
Right. Let's say Piper originally built PA-18 Super Cubs with cotton. But later, Piper went through the FAA process to get approval to switch their production line to using Dacron polyester. Once that happens, using Dacron becomes part of the official, updated TCDS for the PA-18.
Ah, so now Dacron is an approved material for that model according to the manufacturer's own data.
Exactly. And this has a really important implication for how the work is classified. If you recover an older PA-18 using the materials listed on the current updated TCDS, it's classified simply as a major repair.
Not an alteration, even though it's different from how that specific plane left the factory decades ago.
Correct, because the type design itself has been officially updated by the TC holder to include the new material. But if you used polyester under an STC or field approval, that would be a major alteration.
Okay, that distinction is key. Major repair versus major alteration. Where is that officially defined?
That's laid out in the regulations, specifically 14 CFR Part 43, Appendix A. This appendix lists what constitutes major versus minor repairs and alterations.
And fabric work falls under.
General fabric recovering, meaning replacing old fabric with the same type originally approved, like old cotton with new grade A cotton or old polyester with new polyester under its existing STC, that's defined as a major repair.
Okay, but changing the type.
Changing the fundamental type of material, like going from the original cotton to a modern polyester system using an STC or field approval, that is classified as a major alteration.
Okay, wait, I got to push back on that just for clarity because it seems backward to someone outside aviation. You're taking an older, weaker, more flammable material, cotton, and replacing it with something objectively stronger, longer lasting, and safer polyester. Yet legally, that's the bigger deal. That's the alteration.
Precisely. Because you are altering the aircraft from its original certified configuration. The FAA's logic is based on adherence to the type certificate as it was initially issued for that serial number aircraft. Even if the new material is better, it's still a change from the approved type design, hence major alteration.
Got it. Legal logic, not just engineering logic.
You nailed it. And because it's a major alteration, it absolutely requires that FAA Form 337 to be completed, approved, and filed before the aircraft is legal to fly again.
And that Form 337 process usually involves an IA, right? An A&P with inspection authorization.
Always. For a major alteration or a major repair performed by someone other than a certified repair station, the IA's involvement is non-negotiable.
What's their specific role in a recover job?
The IA has to inspect the work. Critically, they must inspect the airframe structure before it gets covered up. Then they often inspect at various stages during the process to ensure you're following every single detail of the STC data or the field approval.
They're verifying compliance.
Absolutely. They have to sign Block 6 of the Form 337 for a major alteration, signifying they inspected it and found it conforms. If it was a field approval, the FAA inspector also signs Block 3. Once the work is done, the A&P mechanic who performed or supervised the work signs the logbook entry referencing the approved Form 337, and the IA signs Block 7 on the 337, approving the aircraft for return to service.
So multiple layers of sign-offs, ensuring it was done right and legally.
Yes. That IA is essentially putting their license on the line, certifying that the procedure was followed perfectly according to the approved data. It's a huge responsibility.
Okay, let's pivot back to the materials themselves. We know we can't substitute things willy-nilly. What are the actual technical specs? What makes a fabric officially airworthy?
It all starts with FAA approval for every single component in the system you're using. The fabric, tapes, threads, cords, glues, coatings, everything. It has to be part of the approved data package, whether that's from the manufacturer, an STC, or a field approval.
No mixing and matching allowed.
Absolutely forbidden. The historical benchmark for strength was set by Technical Standard Order TSOC 15D, which defined aircraft fabric, grade A. That was the standard for high-performance cotton. Any modern fabric intended to replace grade A cotton has to meet or exceed those strength criteria.
And that's where the brand names we mentioned come in. Seconite, polyfiber.
Exactly. Those approved polyester fabrics are manufactured under a Parts Manufacturer Approval, or PMA. That means the FAA has audited and approved the company's manufacturing process itself.
So the fabric roll comes with paperwork.
Yes, and typically these fabrics are sold as part of a complete system covered by an STC, which, as we said, details all the companion materials, the specific tapes, cements, coatings, and the procedures you have to use with that specific fabric. You're buying the whole approved package.
Okay, now for maybe the most critical rule you need to know for inspections. How strong does the fabric have to stay?
This is the absolute bottom line for airworthiness during inspection. Fabric is legally considered airworthy only until its tensile breaking strength deteriorates to less than 70% of the strength required for new fabric on that specific aircraft.
70%, that's the magic number.
That's the line in the sand. Below 70% of the required new strength, it's unairworthy, needs replacement or repair.
So for context, what was the new strength requirement for that old grade A cotton?
Grade A cotton was required to have a new breaking strength of 80 pounds per inch of width.
Okay, so applying the 70% rule, 70% of 80 pounds is 56 pounds. So if that cotton tested below 56 pounds, it was done.
Exactly. Unairworthy. And that minimum strength isn't just pulled out of thin air. It's directly tied to the aerodynamic loads the aircraft experiences in flight.
Based on how fast it flies, how much load the wings carry.
Precisely. It depends on the aircraft's performance, specifically its wing loading, pounds per square foot of wing area, and its never exceed speed, or VNE. The regulations break it down into 3 tiers.
Okay, what's Tier 1, the highest performance?
Tier 1 is for high-performance aircraft, defined as having a wing loading of 9 pounds per square foot or more, or a VNE of 160 mil or more. These planes need the strongest fabric. The requirement is for new fabric strength of at least 80 pounds.
Which means the minimum airworthy strength, that 70% mark, is 56 pounds, same as old grade A cotton.
Correct. Now, Tier 2 is medium performance aircraft. That's wing loading less than 9 pounds per square foot, or VNE less than 160 mile per hour. Most classic Pipers and Cessnas fall in here.
Okay, what's the requirement for them?
They need a minimum new fabric strength of 65 pounds.
And 70% of 65 is about 45.5, so 46 pounds minimum airworthy strength.
Right around 46 pounds, yes. Below that, it's got to be replaced.
And the third tier, the lightest planes.
Tier 3 covers lighter weight aircraft, think gliders, light sport aircraft, maybe some very early utility types, defined as wing loading less than 8 pounds per square foot, or VNE less than 135 miles per hour.
And their requirement?
Minimum new strength is 50 pounds.
Making the 70% airworthiness threshold 35 pounds.
35 pounds. That's the absolute minimum braking strength allowed for fabric on those aircraft during inspection. These numbers 8056, 6546, 503-5 are critical for you to know as an AMT.
Absolutely. Okay, before we even think about putting fabric on the plane, we need the right vocabulary. You mentioned warp and fill.
Yeah, knowing the fabric's construction is key. Warp refers to the threads running the length of the fabric roll. This is usually the stronger direction.
Right.
Fill, sometimes called weave, refers to the threads running across the width of the roll.
Got it. Length is warp, width is fill. What about count?
Count is just the density. It's the number of threads per inch, usually written like warp threads, X fill threads, maybe 60 by 60 or 80 by 80. Higher count generally means a smoother finish and potentially higher strength.
And bias. I hear that term a lot with fabric.
Bias just means a cut or fold or a seam that's made diagonally across the fabric, usually at 45 degrees to the warp and fill threads.
Why do that?
It's essential for covering curves smoothly. A bias cut allows the fabric to stretch and conform around things like wingtips or fuselage corners without puckering or creating stress points. Very important for tapes used on curves.
Makes sense. And edge treatments. Pinked edge.
A picked edge is that zigzag V-cut pattern you see on some tapes or fabric edges. It's made with special shears, and its whole purpose is to stop the fabric from unraveling or fraying after it's cut.
And the selvage edge.
That's the finished edge along the sides of the fabric roll as it comes off the loom. It's woven specifically to prevent unraveling. You usually try to hide the selvage edge under a tape or seam.
Okay. One more term. Greige. It sounds like a color.
Yeah, it does. Greige, pronounced gray or greige,
Yeah.
is the technical term for polyester fabric in its raw loom state before it's been heat shrunk or treated in any way.
The unshrunk condition.
Yeah.
Got it. And cross-coat.
Cross-coat just refers to how you apply liquids, like dope or sealer. You apply the first coat in one direction, let it dry, then apply the second coat at a 90-degree angle to the first. Ensures even coverage and saturation.
Okay, terminology down.
Yeah.
Now, what about all the other materials besides the main fabric? Tapes, fasteners.
Right. These supporting materials are just as critical, and they go on in a specific order. First up, even before the fabric, is anti-chafe tape.
Anti-chafe. So it stops rubbing.
Exactly. It's usually a self-adhesive cloth tape you stick directly onto the airframe structure over sharp metal edges, rivet heads, rib caps, anywhere the main fabric might rub against the structure due to vibration or flexing in flight.
So it's like putting down padding first.
That's a great way to think of it. It prevents the structure from eventually wearing a hole right through your nice new fabric cover from the inside out. Preventative maintenance, basically.
Okay, what goes on next? Still before the main fabric.
Often, especially on wings, you'll apply rib bracing tape.
Bracing tape. To hold the ribs together?
Sort of. It's applied span-wise along the length of the wing, also before the fabric. And the technique is important. You wrap it alternately around the top rib cap, then the bottom rib cap, then the top, then the bottom, zigzagging down the rib.
Why do that?
Because when you tauten the main fabric covering, especially older dope systems that shrink over time or even heat-shrinking polyester, it puts enormous inward pressure on the ribs. This bracing tape helps hold all the ribs in their correct alignment, preventing them from twisting or bowing sideways under that load during the covering process.
Keeps everything straight while you tighten the skin. Clever.
Very important for structural integrity.
Okay, structure prepped, anti-chafe on, bracing tape on. Now the fabric goes on, gets cemented, gets tautened. What tapes go on after that?
Once the main fabric is secure and tight, you apply reinforcing tape. This goes directly over the fabric right on top of the rib cap.
Reinforcing. For what?
It strengthens the area where you're going to do the rib lacing, punching the needle and cord through, or where you might install mechanical fasteners like screws or clips. Those areas take a lot of concentrated load from the airflow trying to pull the fabric off the ribs. The reinforcing tape spreads that load and prevents the lacing cord or fasteners from tearing through the main fabric skin.
Makes sense. Does the width matter?
Critically, the reinforcing tape must be the exact same width as the rib cap underneath it.
Why so specific?
If the tape is too narrow, you create a stress point right along its edge, which can lead to the finish cracking later. If it's too wide, it creates an ugly, visible bulge under the final surface tapes and paint. Precision here is key for both strength and finish quality.
Okay, reinforcing tape on the ribs. What's the final layer of tape, the one we actually see?
That's the surface tape, sometimes called finishing tape. This is the last tape applied. It goes over everything, all the seams between fabric panels, over the reinforcing tape on the ribs, around patches, along leading and trailing edges.
So its job is mainly cosmetic and aerodynamic smoothing.
Primarily, yes. It covers all the underlying work and provides that smooth, finished look. It usually comes in rolls with straight edges or pinked edges. And very importantly, if you're taping around curves like wingtips, you must use bias cut surface tape.
Because bias stretches around curves smoothly.
Exactly. Straight cut tape will just wrinkle and pucker if you try to force it around a tight curve. Bias tape lays down flat.
Okay, tape's covered. How do we actually attach the fabric to the ribs? You mentioned lacing.
Right. The traditional and very common method is rib lacing cord. This is strong cord, usually polyester or LAN, that you literally use to sew or lace the fabric directly to the rib structure underneath. This physically transfers the aerodynamic lift and drag loads from the fabric skin into the main structure.
Is there just one kind of cord?
No, it typically comes in two types. Round cord, which is a bit easier to handle and pull through the holes, or flat braided cord, which costs a bit more but leaves a slightly smoother bump under the surface tape for a nicer finish.
And some planes use screws or clips instead.
Yes, some aircraft designs, especially later ones, use approved mechanical fasteners, special clips, screws, sometimes rivets, often with plastic or aluminum washers under them, instead of cord lacing. You must use whatever method is specified in the aircraft's maintenance manual or the covering STC.
Got it. What about hardware needed for access or drainage after the covering is done?
You need ways to let water out and look inside. For drainage, you install grommets. These are small reinforced rings, usually plastic or aluminum, that get doped or glued into the fabric at the lowest points of the structure, bottom of the fuselage, trailing edge of the wings, to let trapped moisture or condensation escape.
Prevents water from pooling inside.
Right. And there's a special type mentioned, seaplane grommets. They have a little shield or hood over the hole.
Why the shield?
It helps prevent water from splashing up into the structure when the seaplane is on the water, but the airflow over the shield actually helps siphon moisture out when flying. Pretty neat design.
Okay, drains covered. How do you look inside without cutting a giant hole?
For that, you use inspection rings. These are larger rings, typically about 3 inches inside diameter, also doped or glued onto the fabric surface. They provide a reinforced edge, like a porthole rim.
So you can cut the fabric inside the ring for access.
Exactly. You can cut out the fabric disc inside the ring to get a look at or access to important bits of structure underneath. Control pulleys, cables, bell cranks, maybe check for corrosion. Then you can patch the hole using a cover designed for that ring.
Where do you put these rings?
Their locations are usually shown on the manufacturer's drawings. If not, the mechanic uses their judgment, placing them based on where access is needed for inspection and maintenance, often mirroring where they were on the old covering.
Okay, one last small item. Gussets.
Gussets are basically small, shaped patches of fabric, often multi-layered, that are doped or cemented on to reinforce areas where things have to poke through the main fabric, covering like control cable guides, strut attachment points, wires, things like that. They just add strength around those necessary openings.
Right, reinforcing any necessary hole.
Okay.
Okay, lots of prep and pieces. Now, the actual process of putting it all together.
It starts, as we hinted, with meticulous airframe preparation. First step, get the old fabric off. Carefully.
How do you do that without damaging the structure underneath?
You cut it away, usually with a sharp knife, being really careful not to gouge the tubing or wood. Smart mechanics often try to remove large sections of the old fabric reasonably intact.
Why keep the old stuff?
It makes a perfect template. You can lay it out and mark exactly where all the inspection rings, drain grommets, and other features were located. Saves a ton of measuring on the new fabric.
Good tip. Any safety warnings during removal?
Huge GE one. Before you start pulling or tearing the old fabric off, you absolutely must find and cut or remove all the old rib stitching cords or fasteners. If you just try to rip the fabric off with those still attached, the tension and the sharp edges of clips can easily snag and damage the underlying rib structure. Very important safety step.
Okay, old fabric off, fasteners cut. Now you have a bare airframe.
Yep. And this is your one big chance for a thorough inspection. You need to clean everything meticulously. Solvents like MEK, methyl ethyl ketone, are often used to get rid of stubborn old adhesive residue, but you need good ventilation and proper PPE.
Check for corrosion, damage.
Everything. Any cracks, dents, bent tubes, rotten wood, corrosion. All repairs and treatments must be done now before you cover it up again. If you cover over hidden corrosion, you're just asking for trouble down the road.
Makes sense.
Yeah.
Once it's clean and repaired, do you prime it?
Yes, absolutely. This step is often called dope proofing. The exposed structure, whether it's wood or metal, must be primed or varnished with a compatible coating before the new fabric goes on.
Why is that so critical?
Because the cements and sealers used with modern fabric systems contain powerful solvents. If you use the wrong kind of primer, like an old-style single-part zinc chromate, the solvents in the fabric cement can actually dissolve the primer's binder.
And the fabric just lets go.
Exactly. The fabric could detach from the structure as the cement cures or later in service. Big problem. You typically need to use materials specified by the STC, often 2-part epoxy primers, or specific varnishes that won't be affected by the covering system's chemicals.
Okay, primed and ready. Any special prep for specific areas like the leading edge?
Oh yeah, the leading edge is super critical for aerodynamics, for smooth airflow, for generating lift properly. If it's a plywood leading edge, it needs to be sanded perfectly smooth, no ridges or bumps.
And if it's an aluminum wing?
Sometimes the STC will require you to apply approved felt strips or even thin polyester padding over the metal leading edge ribs before the fabric goes on. This ensures a smooth contour and can also act as a buffer between the metal and the fabric cement.
Okay, structure's totally prepped.
Yeah.
How do we actually apply the fabric? Are there different methods?
2 main methods. The traditional one is the blanket method.
Blanket. like laying sheets on.
Pretty much. You cut large, flat sections or blankets of fabric. You drape them over the structure, trim them to fit, and then cement them down, usually with overlapping seams where the pieces meet. A large wing, for instance, might need two big blankets, one top, one bottom, with overlaps at the leading and trailing edges and maybe the tip.
Sounds like it requires careful cutting and fitting.
It does. It takes skill. The alternative, which saves a lot of time, is the envelope method,
Envelope.
like a pillowcase.
Exactly like that. You buy pre-sewn envelopes of fabric specifically made for your aircraft model's wing or fuselage or tail surface. You just slide the envelope over the structure like putting on a sock or pillowcase.
That sounds way faster.
It is, but the catch is those sewn seams have to meet specific FAA-approved standards, usually detailed in AC 43.13-1 or the Covering Systems STC. And the seams have to be located strategically, usually over a rib or stringer or along an edge like the trailing edge where they don't disrupt airflow too much.
Okay, speaking of seams, whether they're sewn or glued, what are the requirements?
For modern polyester systems using the blanket method, almost all seams are doped or glued. They provide plenty of strength and elasticity. The amount of overlap is specified by the STC.
Is it always the same overlap?
No, it varies. In critical airflow areas, like along the leading edge, you typically need a wider overlap, maybe 2 to 4 inches minimum, to handle the higher loads. In less critical areas, like maybe a seam on the fuselage side, 1 to 2 inches might be sufficient. Again, follow the STC. And where do you try to put these seams aesthetically?
Generally for looks and maybe slight drag reduction, you try to hide them. On a high-wing plane, you'd often put major seams on the top surfaces where they're less visible from the ground. On a low-wing plane, you'd put them on the bottom. And a quick warning about sewn seams, especially with the envelope method. If the seam is particularly thick or bulky and it ends up right near the leading edge of a thinner wing, it can actually act like an unintended stall strip.
Oh, tripping the airflow early.
Yeah, potentially affecting the stall characteristics at low speeds. Something to be aware of with seam placement.
Okay, fabric is laid out, seams are planned. How do you actually stick it down and tighten it? Cementing first.
Right. The cementing process secures the fabric to the underlying structure, the ribs, spars, longerons. The typical technique involves applying a couple of coats of the approved adhesive to the structure first and letting those pre-coats dry completely. Then, just before you lay the fabric down, you apply a fresh, wet coat of cement onto those dried pre-coats. You position the fabric onto this wet bed, smooth it out, maybe use some temporary clamps or weights, and let the cement cure, bonding the fabric to the structure.
Is that the only way? I thought I heard about heat activation.
You're probably thinking of the Stewart system. That's a popular waterborne system, and it uses a different approach. With Stewart's, you apply the pre-coats and let them dry fully, position the fabric, and then you use your calibrated heat iron through the fabric to reactivate the dried cement underneath, creating the bond. No wet bed involved. Again, follow the specific STC instructions.
Okay, cemented down. Now for tightening. With polyester, that means heat shrinking, right?
Yes, heat shrinking is the key step for polyester, and you absolutely must use a properly calibrated fabric iron with accurate temperature control.
Why is the temperature so critical?
Because the amount the polyester shrinks is directly related to the temperature you apply. It's a precise process. For example, a fabric might shrink only a little, maybe 5% at 250 degrees Fahrenheit, but shrink significantly more, maybe 10% at 350 degrees Fahrenheit.
So you have to know the target temperature for the system you're using.
Exactly. The STC will specify the shrinking temperature, or maybe a range of temperatures. You usually do it in stages. First, a lower temperature pass, maybe around 225 degrees air, just to get rid of wrinkles and make the fabric snug. Then you come back with the final higher shrinking temperature, say 300 degrees or 350 degrees, whatever the STC calls for, to achieve the final required tautness.
Do you just iron it smoothly from one end to the other?
Absolutely not. That's a classic rookie mistake. If you just iron sequentially down a wing, for example, you'll pull all the tension towards one end and potentially warp the whole structure, pulling ribs out of alignment.
So how do you do it?
You have to constantly skip and alternate. Start shrinking a bit at one end, then immediately go to the opposite end or the opposite side, then maybe do a section in the middle. Keep jumping around back and forth, top and bottom, gradually bringing the whole surface up to tension evenly.
Balancing the tension across the structure.
Precisely. It prevents you from inducing warps or twists into the airframe. Critical technique.
Okay, fabric is smooth, tight, and hopefully straight. But cement alone isn't enough to hold it against flight loads, right? That's where rib lacing comes in.
Correct. Cement holds the fabric to the structure. But rib lacing, or approved mechanical fasteners, are what really transfers those big aerodynamic loads, hundreds of pounds of lift on a wing panel, from the fabric skin into the ribs and spars. You can't skip this step.
And how close together do the stitches or fasteners need to be?
The spacing is critical and must follow the manufacturer's original data, the STC instructions, or if neither of those is available, the charts provided in Advisory Circular 43.13-1.
Is the spacing uniform everywhere?
No, there's one area that requires closer spacing. The slipstream area.
Behind the propeller.
Exactly. The air coming off the prop is much more turbulent and has higher dynamic pressure. So the fabric in that area experiences higher loads. The rule is you need closer lacing spacing across the width of the propeller, plus one additional rib bay on either side of the prop's path.
Okay, closer spacing in the slipstream. How do you actually do the lacing?
You use a special long curved upholstery-type needle. You pass the approved lacing cord down through the top fabric, through pre-drilled holes in the rib cap, and then up through the bottom fabric, basically sewing the top and bottom skins together through the rib.
And you tie knots at each point.
Yes, and the type of knot is extremely important for safety. You typically start the lace run with a secure knot, like a square knot secured with an extra half hitch. Then each subsequent stitch down the rib uses a specific knot called the modified seine knot.
Modified seine knot, why that specific knot?
Because the modified seine knot locks itself tightly at each individual stitch location. It prevents the tension from slipping along the cord down the lengths of the rib. If you used a simply knot, tightening one stitch could loosen the previous ones, potentially allowing the whole rib to get pulled out of alignment.
So each knot is independent.
Yes, and for a really clean look, experienced technicians often use hidden modified seine knots, where they manage to tuck the bulky part of the knot down below the fabric surface, leaving only a single smooth strand of cord visible across the rib cap. Takes practice, but it looks very professional. Mastering that knot sequence is absolutely fundamental for anyone doing fabric work.
Definitely sounds like it.
Yeah.
Okay, fabric attached, lace tight. Now we have to protect it, right? Back to the chemicals, the coating system. What's the sequence?
The sequence is critical for longevity and adhesion. It usually starts with the fabric sealer.
Sealer, what's his job?
First coat, often brushed on, maybe in a cross-coat pattern, to really saturate the polyester fibers. Its job is twofold. First, create a barrier against moisture and contaminants getting into the fabric weave. Second, provide a really good base layer that subsequent coats will stick to reliably.
And this is usually non-tautening, right? To avoid shrinking the fabric even more.
Yes, very important. After heap shrinking, you don't want the chemical coats to add significant extra tension. So use a non-tautening dope formula or a proprietary sealer specifically designed for this first step, preventing excess stress on the airframe.
Okay, sealed. What's next? The UV protection.
Exactly. Next come the filler coats, sometimes called UV block coats. These are absolutely critical. They're applied in multiple layers, often cross-coated again.
And these contain the aluminum powder or other blockers.
Yes. These coats contain the solids aluminum paste, sometimes carbon black, or modern chemical UV absorbers that physically block the ultraviolet light from ever reaching the polyester fabric underneath.
Because UV is the polyester's main enemy.
It's the single most destructive element for polyester fabric longevity. If UV gets through, the fabric strength degrades over time, even if it looks okay. A good opaque filler layer is the key to making polyester last practically forever.
Do some systems combine the sealer and filler?
Yes, some modern systems have products that act as both sealer and filler, sometimes called a fabric primer. They go on after all the surface tapes are applied. Again, follow the specific STC.
Okay, sealed, UV blocked. Now for the pretty part. The top coats.
Right. The top coats provide the final color and gloss. These might be traditional colored butyrate dope, or more commonly today, modern polyurethane or enamel paints specifically formulated for use over fabric systems.
Compatibility is key here too, I assume.
Absolutely paramount. The top coat must be chemically compatible with the filler coats underneath it. Using the wrong type of paint over a specific filler system can cause lifting, bubbling, cracking, a total mess. You have to stick strictly to the combinations approved in the STC.
What about additives? Thinners, retarders?
Only approved additives specified by the STC are allowed. You'll use thinners to get the right spraying viscosity. You might need retarders if you're spraying in high humidity.
Retarders slow down drying. Why?
Yes. If dope or paint dries too quickly in humid air, moisture can condense on the surface as it cools from evaporation, causing a milky white discoloration called blushing. Retarders slow the drying, giving the moisture time to escape.
Makes sense. Any others?
You might use accelerators to speed up drying in cool weather, or catalysts required for some two-part polyurethane systems. And one important caution: rejuvenator.
What's that for?
Rejuvenator is a special solvent blend designed to soften old, brittle butyrate dope finishes, allowing the plasticizers within it to redistribute and restore some flexibility. It is only for dope finishes. If you spray rejuvenator onto a modern polyurethane top coat, you will likely destroy the finish. Big mistake.
Good to know. Okay, fast forward. The plane's been flying for years. It's annual inspection time. How do you check if that fabric is still airworthy, still above that 70% strength?
The classic FAA accepted method, if the manufacturer provides no other specific guidance, is the test strip method. And yes, it's destructive.
Destructive how? You have to cut the fabric?
Yep. Following AC 43.13-, you typically cut a small strip, about 1¼ inches wide by maybe 4 to 6 inches long, from an area likely to be most degraded.
Where's that usually?
Often the top surface of the wing or horizontal stabilizer, especially if it's a dark color, because that gets the most sun exposure, the most UV damage.
Okay, you cut the strip, then what?
Then the hard part. You have to carefully remove all the coatings, the paint, the fillers, the sealer, usually by soaking the strip in a strong solvent like MEK until you're down to the bare fabric fibers. Then you carefully unravel the edges until the strip is exactly 1 inch wide.
Precision matters.
Absolutely. Then you clamp one end in a fixture and hang weights from the other end, adding weight incrementally until the fabric strip breaks. The weight it held just before breaking is its tensile strength.
And you compare that number to the 70% threshold for that aircraft type.
Exactly. If it breaks below that 70% minimum, 56 pounds, 46 pounds, or 35 pounds, depending on the plane, the fabric in that area is unairworthy.
But wait, you're testing one tiny strip from potentially the worst spot on the whole plane? How representative is that of the overall condition?
That's a very valid point and a known limitation of the strip test. The FAA accepts it, but it's not perfect. And that's exactly why the manufacturers of modern polyester systems like Polyfiber and Seconite got FAA approval for an alternative, non-destructive test method in their STCs.
Non-destructive. How does that work? No cutting.
No cutting. The logic is based on the integrity of the UV blocking filler coats. The idea is, if the UV protection layer is still intact and doing its job, then the polyester fabric underneath, which doesn't rot, should still have close to its original strength.
Okay, so how do you check the UV protection without cutting?
It's usually a two-part check. First, a really thorough visual inspection. You look closely at the finish. Is it consistent? Is it flexible? Or is it showing signs of cracking or crazing? You also do the knuckle test. Push hard on the fabric with your knuckles between ribs. It should indent flexibly, but not crack or make popping sounds.
Okay, visual and feel. What's the second part?
The light test. This is the key. You remove an inspection panel or access cover. Then you shine a bright light, like a 60-watt bulb or a strong flashlight, held about a foot away from the outside surface of the fabric. You look from the inside.
And what are you looking for?
You're looking to see if any light comes through the fabric. The standard is no light should be visible. If you can't see the light source through the fabric weave, it means the opaque UV-blocking filler coats are still intact and protecting the fabric. In that case, the fabric is considered airworthy under those STCs.
And if you can see light coming through?
If light is visible, it means the UV protection is compromised. The fabric has likely been exposed and potentially degraded. In that situation, the non-destructive test fails, and you must proceed to do a destructive strip test to determine the actual remaining strength.
Got it. What about those mechanical punch testers I sometimes see? The Mall tester or See-Both tester. Are they approved?
No. Let me be clear. Those devices are not FAA approved for determining fabric airworthiness. They are spring-loaded devices that punch the fabric with a blunt point and give a reading based on the pressure needed.
So why do people use them?
A mechanic might use one at their own discretion to get a quick general opinion of the fabric's condition, maybe test a few spots quickly, but the accuracy is highly variable. It depends on the tester's calibration, the thickness and hardness of the paint, how brittle the top coat is, lots of factors.
So not a substitute for the real tests?
Absolutely not. If a punch tester gives a reading anywhere near that 70% minimum breaking strength, it's basically telling you that you must go do a proper approved test, either the light test if applicable, or definitely a strip test, to make the legal airworthiness determination.
Okay, last area. Repairs. Sometimes damage happens. Punctures, tears. Do you always patch it, or sometimes you just have to recover the whole thing?
That's a judgment call. You have to consider the extent of the damage, obviously, but also what's the overall condition and estimated remaining lifespan of the rest of the covering. If the fabric is generally old and near the end of its life, patching might just be delaying the inevitable recover.
What about tautness? Can that force a recover?
Yes, particularly with older dope finishes that tend to shrink continuously over decades. If the fabric becomes excessively taut, it can actually start to distort or damage the underlying airframe structure, bowing ribs, compressing spars. If you see signs of that, patching isn't the answer. A full recovery is needed to relieve that stress.
Assuming a patch is okay for modern polyester, how is it done? Sewing.
Almost never sewing for polyester repairs these days. The preferred method is almost always a cemented patch, following the specific STC procedures. Sewing is more of a legacy technique from the cotton days.
Okay, cemented patch. Is there one standard way to do it?
No, and this is absolutely critical from a regulatory standpoint. The exact technique for preparing the area and applying the patch depends entirely on which proprietary covering system, which STC was used to cover the aircraft originally.
How do they differ?
Some systems, like polyfiber, might require you to chemically strip all the old coatings off the damaged area right down to the bare fabric before applying the patch with their specific cement. Other systems, like Sikanite with certain top coats, might allow you to just thoroughly scuff the existing topcoat surface before cementing the patch over it.
And using the wrong technique is bad.
It's unairworthy. If you use a polyfiber repair procedure on a plane that was covered using the Sikanite STC or vice versa, that repair does not meet the approved data, and the aircraft is not legal to fly even if the patch looks perfect. You must know which system is on the aircraft and use that system's specific approved repair procedure.
That seems like a major trap for the unwary.
It is. Documentation is key. And one final point on repairs. If the damage is large, requiring you to replace a whole panel of fabric, say between two wing ribs from leading edge to trailing edge, that's generally considered a major repair.
Which means
It requires proper documentation, likely including an FAA Form 337, just like the initial covering job might have. Check the regs and the STC.
wow. Okay, we've covered a ton of ground here, right from early linen and nitrate dope all the way to modern polyester systems and their specific repair needs.
We really hit the key points from Chapter 3, that material evolution driven by flammability and durability issues. Then the 3 legal paths for using modern materials, STC, field approval, TCDS update, and understanding major repair versus major alteration.
And that hard line for airworthiness, the fabric strength has to stay above 70% of the required new strength for that aircraft type.
Right. And underlying all of it, especially with the modern systems, is the absolute need for precision and adherence to the specific STC. It's not just the fabric, it's the right tapes, the right cements, the right coatings, the right thinners, the right cure times, the right repair techniques, all specified, all mandatory.
That precision, as you said, is the difference between doing it right and making a very expensive or worse, dangerous mistake.
Exactly. The sheer variety now dope-based finishes, polyurethanes, even waterborne systems like Stewart's means you can't assume one process works for all. You have to follow the specific approved data for the system you're working with. That's the job.
Okay, final thought for our listeners, the AMT students working through this. We talked about how surface tape provides that smooth finish. And the source notes that if a piece of surface tape comes loose on a movable control surface, like an aileron or elevator, it can act like an unintended trim tab, right? Seriously affecting how the plane flies.
Yeah, that's a well-known hazard. Can cause unexpected roll or pitch.
But the source gives one more little nugget. What happens if that tape comes loose on a fixed surface, like the main part of the wing, maybe out near the tip? It says it acts as a spoiler.
Disrupting the airflow over that section of the wing.
Exactly. So think about that. A simple piece of loose tape creating an unwanted spoiler. What could that do? Maybe cause asymmetric lift during a stall. Maybe just add drag. It really drives home how even that final, seemingly cosmetic layer of tape needs meticulous application and inspection every time. That attention to detail is what makes a safe, professional AMT.